became a pro in the concept of early effect. So watch this effect and know each and every time that what is contributing the early effect, what is mean by early effect, what will be the impact of this in the IV curve, and what are the criteria that we need to consider because of the early effects. So let's get it into this concept. So we know, so on exchange we have taken NPN transistor instead of PNP transistor. So there is nothing to be worried. So this is a JE, this is JC. So we know that we will be giving forward potential here and reverse potential here, reverse bias is here. So we know whenever there is a reverse bias, there will be depletion rate. So the thing, the red color I have highlighted, right? So this is the depletion width. So because of the reverse potential. So we know that this is a thin depletion region, and there is nothing will be contributed much there because the reverse bias saturation will be that kind of things. So based on the thing that we can take into account that the holes which are majority charge carrier from the emitter region will be traversed to the collector. So that will not be a problem. So some here you see there is some quiet region where there is no depletion width. So whenever this is happening, so fewer number of majority charge carrier that are coming here will be recombined. So there is one more effect that we are taken into account, that whenever we are increasing the reverse bias concentration. For an example, here this is VCB, right? So VCB. So whenever we are increasing VCB, so when VCBs keep on increasing, then what will happen? The depletion width will be keep on increasing, right? So if the depletion width is keep on increasing, then the WB dash will be keep on decreasing. So this is the actual width of the base region. So WB dash is the non-depleted region. So WB is the actual width of the base region. So that will be usually very thin. So if for a considerable amount of reverse saturation, reverse bias potential itself, the depletion width will be vanished. So then this will happen what? The recombination will decrease. So because the width is decreasing, so the recombination will be also decrease. So recombination inside base region will decrease. So recombination inside WB will decrease. So which will cause what? So which will cause IB to decrease. So if IB is decreasing, no recombination happening, so all the current, all the majority charge carrier that were created are pushed to collector. So this will cause IC to increase much more, right? So this is the cause. So you guys may think, so we are getting more IC, so this is benefit. So that will affect in some other term. So I will let you know, so what will happen there. So this is the first analogy that you have to consider. So if we keep on increasing the width of the, if we keep on increasing the reverse potential, the depletion rates will be further increased. So based upon this increase, so what are the majority charge carrier that are here? So that will be diffused through here. So no recombination will happen. So you guys may think, so if it is reverse bias, how the potential will come? So here you see here the majority charge carrier is N type, here the majority charge carrier is N type. So if this is completely depleted, so both are seems to be at the same conductor. So there will be no effect. So directly a majority charge carrier to majority charge carrier. So there is no minority charge carrier interaction which is happening. So that is what the effect that is doing. So early effect. So let's discuss more thing on this. So how this is affecting IV curve. So all the things we will be discuss more. So don't worry. So what are the IC, which IC will be keep on increasing, and one more thing is that IE will be prox equal to IC. So there is no recombination inside the WB region. So means what will happen? So it will be keep on increasing the IC's current. So there is no depletion or no recombination inside the thing. So next thing is that we know alpha already. So that is an common base current gain. So we know that is IC by IE. So this is in common base mode. So similarly we have our common emitter. Similarly we have for common collector. So common emitter will be called as beta. So which will be IC divided by IB. So you know, if emitter is common, then output is taken at IC and input is IB. So these difference configuration we will be look back soon. So stay tuned guys. So gamma at the collector, these are current gain. So this is current gain, not voltage gain. So only we are for now we are worrying about current gains only. So later we can discuss those things. So this is current gain. So if collector is common, then what will be the thing? So IE which is the output and IB which is the input. So this is what thing. So the thing is that alpha which is equal to IC plus IE. So if IC is keep on increasing, IE will also increase because of that effect. So then which will cause the alpha to increase. So this is one effect. So because of the because of the early effect, so we are facing this issue. So here also you can see, so if we keep on increasing IC, so then beta will increase. So beta will also increase. So if we keep on increasing the IC is also equal to IE. So gamma will also increase. So because of the early effect, we are facing all the current gains to increase. So because of early effects, what happened? So all the current gain ratios are increasing. So we are getting an BJT with a specific parameter, but because of this early effect, all the transistors current gain are increasing, then we may not lead into our perfect region of expectation. So as the reverse bias at the collector junction keep on increasing, then at a particular reverse bias, the complete base region will be depleted. Okay, so complete base region will be depleted. So there will be one point where WB dash will be proxy equal to 0. So that region which is called as punch through. So this is a very important question. So please make note of it. So even many core interviews they ask what does mean by punch through or things punch through or reach through condition or reach through. Okay, so please make note of it. In this condition, very large current flows through the transistor and BJT will be damaged. So now the thing is that BJT will be burned. Simply we can say BJT will be get burned and get damaged. So this thing we need to be avoiding. So this is one of the key criteria. So BJT will be burned off. So it will not work properly. In most of the practical transistor, before punch through, avalanche breakthrough will occur. So this punch through will happen, but before that avalanche break will occur because breakdown the BJT will be gone, so it won't work properly. So let me draw the characteristic curve, IV characteristic curve. How before that let me draw how the transistor will look, how the transistor representation. So this is how we will be representing the transistor. Okay, so let me name everything. So this is B base, this is collector, this is emitter. Okay, so this potential which is VBE. Okay, so on this potential which is VCE. I think you guys are able to see, right? So base E, this is the forward bias potential. This will be mostly equal to 0.7 or 0 thing, that negligible amount only. But this thing, this will be quite greater. So this will be something above greater than 2 or like kind of thing. So IC will flow in this direction. So this will be taken as IE. And here the current will flow as IB. Okay, so if we this is an NPN transistor, then we have to name. So we know that current will flow from P to N. So the NPN transistor, the arrow mark will point outside. So if it is an PNP, then arrow mark will point inside. So this is one of the key criteria to find out whether the transistor is NPN or PNP. So this is very important. So please note on how we can do it. So the output characteristics, how it will look like this. So initially the transistor will act in a linear region. So there will be no change. So if you have to name means, so this is VCE, the reverse potential, and this is IC. So this is the output characteristic, right? So VCE is increases, IC will keep on increases. So this region is the active region. So some point of time, this will be at, it will be saturated. Okay. So ideally what need to happen is that, ideally this need to be like this and 0-degree slope. Okay. So this is how it need to be practically, not actually theoretical. Not theoretical, ideal, we can take it. So ideally it need to be like this, but due to early effect the slope will be there. So after the transition it will be not like this. After here it will be like this. You see, some 12 to 10 degrees of transition, right? So because of this there will be a slope. So this slope is the resistance that we have to take in account. So this is at constant IB. So IB1, this is constant. Okay. So this is due to early effect. So you have to clearly notice the slope that is happening because of early effect. So we already discussed in diode, right? So if there is a slope, then the 1 by slope is the R. So R which is equal to 1 by slope. Okay. So here R is the parameter that we need to take into account. So whenever we are calculating the things. So okay. So IC, our IC formula which is equal to IS e power VBE divided by eta VT minus 1. So this is normal condition without early effect. Without early effect. Okay. So when we are considering the early effect, so see how the formula is modifying. So it's very crucial. So is e power VBE divided by eta VT minus 1. Okay. So if we are considering the early effects, then 1 plus modulus of ECE divided by VA. So VA is the early potential. So okay, so I will explain you where the VA will look like, where the VA will come in picture. So this is with the early effect. So the extra term will be get added here. Okay. So how to find the VA? So VA is the thing. So let me draw it here, or else I can copy paste from here. So this is the thing. So let me extend the y-axis, so x-axis, and let me also expand this one. Actually, it need to align perfectly from here. Okay. So the slope will reach at a point. So the slope will reach at a point. So if you extend the slope of graph, it will meet some at a particular point. So that is the minus VA. So this is the point that we need to take into the early effect thing. The slope of this curve which will be equal to the slope which is equal to IC divided by VA. Okay, so this is the slope that you have to take in. So if we reverse the slope, then R0 which is equal to VA divided by IC. So this R0 is one of the critical factor. So whenever we are modeling the BJT, we need to include it. So please make a note of it. So this is the early voltage. So this graph is very important, guys. So I'm pretty sure that before completing the electronic subject, you guys will be going to this term many times. So you guys need to know. So this is without early effect. So above is with the early effect. So without VA. Okay. So I hope you guys are able to understand. So due to early effect, so many things will be changing. So if early effect, which if early effect is keep on decreasing, means this graph is keep on going outside, or this curve is the VA is coming to this state, then what will happen? The R0 will also decreases because VA this is directly proportional to R0. So if R0 is going, then the slope of the characteristics will keep on increasing. The slope will increase. So if the slope is a 10 degree format, right? So then that will be 45 and then 90 like that. If it is 45, then it is completely the IC will keep on increasing. Then the device will be going into thermal run state and the device will break off. So that is for the thing that you have to take into account. So you may ask a question: how can we reduce this early effect? So only one thing that we can do. So based upon the depletion with the region of region only we can take. So if the base width decreases physically, then we can observe more modular effect. So some practical thing is that so quite we can increase the WB. So without the WB can be increased, but that is not that much feasible solution because WB need to be smaller in order to make all the majority charge carrier need to flow from the emitter to collector region. So that's why we usually won't take that into account. But this is what the something. But usually there will be L effect that we can't avoid it completely. But thing is that this is what because W effect region that is a very thin. So that's why these effects are coming into picture. So I'm leaving here, guys. So I hope we have explained the early effect in a very good way. So I hope you guys are able to get some idea. So this the reverse saturation current, if the reverse bias is completely increasing, then the actual width of the base region will be going to 0 at some point of time. So that point is punched through, but that will not happen. So even if there is a smaller reverse potential and that is quite greater, there will be the thing. So what I'm explaining is that because of this there is even the small depletion which is there, right? So even because of this there will be the early effect, the concentration will vary. So early effect, if there is no early effect means then this depletion with there should not be any reverse bias potential. So that is not possible. So in order to make the transistor working, so we need to apply reverse bias. So there will be the thing. So only thing is that so if we keep on increasing the RB, then only we are in trouble. So with the quite amount of reverse bias, so we can understand or we can avoid these early effects. So similar, if you see, so we know the value effect will be there, but that is to small extent. Or what we can do is that we can work in the transistor in this region. So this is the linear region, right? So this is active region. So this is saturation. So we can make the transistor to work in this region itself. So means the limit is that this one. So this is the VOCE, not VOC. We can't make that. So we can term as VCC. So that is VCC and ICC, like kind of thing we can name it. So this is the operating point of the transistor. So we need to operate the transistor only at this point, because above which it will be going into early effect, or below which the current gain will not be minimum, or current gain will not be that much high. So we need to fix the transistor at some operating point. So that point, which is the maximum output gaining point. So that we will keep detailedly discuss in analog devices. So in the semiconductor physics or electronic devices, we need to just know how the things will work. So for that, this will be fine. So in analog electronics or electrical circuit, whatever you call, so there will be discussing all this criteria again in a very good manner. So I hope this will be understanding for you guys. So please like, share and subscribe the channel. So comment your doubts. I will be posting the answer for all of this. So please stay tuned for the next lectures. Thank you guys.